I'm taking the opportunity to start all over with this slide as we go towards a discussion of strong oxidation for alkenes and alkynes. Remember that there was a time that I discussed this, wherein oxidation can be defined in many ways in organic chemistry, including addition of oxygen, that's the most common sense definition, addition of bond or increase of bond order to oxygen, that is, from a single bond to oxygen to a double bond, or removal of hydrogen. Any of these or combination of these three will qualify as oxidation. And let's see that actually materializing in our oxidation of alkenes and alkynes. So, for example, I have a carbon here that it's not completely drawn as you see. Let's say that this carbon has a double or triple bond. And let me tell you that what you may want to imagine for now is that any hydrogen attached to this carbon is what we can call oxidizable, meaning we can oxidize it. Let's say that this H does not yet exist, and the only bond that I can oxidize is this one bond. What we can utilize with that is to convert this single bond H to a single bond OH. So all I'm trying to say here is that if I have one bond available for oxidation, that will afford us an OH. But let me erase that because let's try a different scenario. Let's say that you have a case wherein you can see both of these bonds, meaning you have two bonds available for oxidation. You can actually convert these two bonds to a double bond to a single O. So that means that if I have two bonds ready for oxidation, I can afford a carbonyl group C double bond O. And that follows our basic rules because oxidation can be addition of oxygen or even an increase in the bond order of oxygen and so on. Oh, by the way, the fact that from OH it becomes a double bond O, there's also the removal of H, which is also oxidation. Now let's say that I'm gonna oxidize this example, and usually later on when we say oxidative cleavage, it means you're gonna break it down, particularly the double bond. So imagine that you have these two bonds ready for oxidation. Well, it's gonna be like this, right? Meaning that these two bonds that I have broken will be a double bond O in transition. But the other things like these two R's, they're not oxidized anyway, so nothing happens to them. I'm not gonna call what this is. You should know how to call this, but I just want you to observe first. Let's say I want to oxidize the same alkene, but this time it has one H, which is pretty much oxidizable, especially with the reagents that I will mention later. That means that not only do I have two bonds to oxidize, but three because of this additional H. The R will stay there. There's nothing that's gonna change there. But that double bond I just broke will become a double bond O. And since I have still one bond left to oxidize, we know that we can convert that to an OH, giving us something like this. Again, hopefully you already know what this is called, but I'm just trying to share you what's happening in general. And finally, I have this possibility wherein, let's say I have this carbon and I break this bond and these two bonds can be oxidized. But the fact that my two remaining bonds are also bonds to H, meaning these two bonds can be also oxidized. So like, what can you imagine coming out from this? Well, in total you have 4, right? And 4, okay, divided by 2 equals 2 pieces of 2 bonds, meaning twice of this or twice of this, meaning that my product here has not just one but two double bond O's. And I think that is logical. Okay, we did a little bit of basic math to get here, but this is what it looks like. Alright, let's call what this is. This one, of course, is called a ketone, RCOR. This one, RCOOH, is called a carboxylic acid. And COO, don't, a lot of people overthink on this, okay? This is just carbon dioxide, okay? So meaning that if I have two bonds that are oxidized, I can afford only a ketone. If I have three bonds that are oxidized, these are the three, I get a carboxylic acid. Although later it can be an aldehyde depending on the reagent. And then if I have all my four bonds to carbon ready to be oxidized, then I can afford carbon dioxide. Now let's get to more specific details. So in oxidative cleavage, what reagents can you use? Normally in textbooks, we have two options. If you only use the word strong oxidation, it uses KMnO4 in the presence of H+. Do note that this is a very important thing to take note of, because if I use KMnO4 not in acid but in base, such as KMnO4 in OH minus, that's how it's usually written, it's a different reaction. Going back here, if you use KMnO4, if you use KMnO4 in OH, what you're gonna do is only mild, as in mild oxidation. But to say that it's strong, meaning it's strong enough that you're gonna break bonds, just like what I showed you here. Break bonds. Okay? Or you can use ozone or O3 in the presence of additional reagents like zinc and acid catalyst, and that reaction would be called ozonolysis. In fact, oxidative cleavage can refer to both, but the idea here is, although you do have some difference in the reagent, the process is gonna be the same. That is, you're gonna split something into two. And note that these reactions, these two reactions, these reagents oxidize all vinylic hydrogens. Remember what I told you a while ago, that just imagine that in this screen all the hydrogens can be oxidized. And I did mention that this carbon has a double bond. Well, let's call them what they are. A carbon with a double bond is called a vinylic carbon, right? So I think it's right for me to call these two hydrogens, let's say, as vinylic hydrogens, right? I'm not really sure personally if textbooks follow that, but we'll just refer to any hydrogen attached to a vinylic carbon as a vinylic hydrogen. And these are oxidizable, as I have been showing you for the last few minutes. And the double bond or triple bond itself is liable for oxidation, which is what I was doing also a while ago. The moment I cut a double bond, that is automatic two bonds that can be oxidized. But in a triple bond, it also applies that if I cut it, that means that these three bonds will automatically be oxidized. So technically speaking, every double bond gives me two oxidizable bonds, or every triple bond affords me three oxidizable bonds. And we have actually discussed this table that if I have two, let's see if it matches. If I have two, do I have a ketone? Yeah, right? If 3, do I have acid or aldehyde? Well, this is acid, this is aldehyde. Yeah. And remember I told you a while ago, it depends on the reagent whether I get an aldehyde and an acid. So now to clarify that, if you use KMnO4 in acid, you get a carboxylic acid. But if you use ozone, you only get an aldehyde. You can just imagine that ozone is kind of milder in terms of oxidation. So it gives an aldehyde instead of a carboxylic acid. Of course, the mechanism is very, very different. But again, we avoid things like that in this discussion, just to simplify things. And for 4 oxidizable bonds, then nothing else but CO2. So in order to observe how this happens, I'm putting here two examples of actual compounds, and let's try to apply things that we learned so far. It's not as easy in the first try, so actually I may upload something in the future which will concentrate only on examples for oxidative cleavage. But here we go with these two examples. So imagine that I'm going to break this. The moment I break this, I have to ask the question, what's going to be the fate of these two vinylic carbons? In order to answer that, then you have to identify how many oxidizable bonds they have. Of course, again, your options are only 2, 3, and 4, okay? So here, it has a double bond, right? So that's already 2 oxidizable bonds. And the fact that you're supposed to know already by structural analysis that there should be one H here that's hiding. So that means I have 1, 2, 3 oxidizable bonds. Meaning that 3, and I use KMnO4, I'm gonna get a carboxylic acid from this portion. So all you need to do really is to copy these carbons. Make sure you copy everything properly. So this one, then a bond to this one, which is this, and then a bond to this. And take note that this is the one that we identified a while ago as having 3 oxidizable bonds. So again, we're gonna have to make that a COOH. I'll just write it in reverse. So yeah, so this is gonna be the product from this half. How about this half? Well, let's analyze. How many bonds are oxidizable here? Double bond is automatic too, right? But of course, you should realize there are also additional 2 hydrogens here. So how many are there in total? Not just 2, but 4. And what's gonna happen if I have 4 oxidizable bonds? It's gonna be CO2. So actually, this thing right here will just be mere carbon dioxide. Okay? Let's have another one. So once again, I have a double bond and I want to break that. But do note that this time we're going to use ozone. Okay, so in case we find 3, we're going to get an aldehyde instead of a carboxylic acid. So first, you should imagine that this bond right here, these 2 bonds will break. And let's count how many OBs we have. I'm going to use a different color just to see it clearer. So for this, how many OBs or oxidizable bonds are there total? This is equivalent to a double bond. The double bond is equivalent to 2, right? Are there any more? Well, the other 2 bonds are bonds to carbon, so they're not counted. So for this, I get 2. So all I have to do is to actually convert that double bond a while ago to a double bond O, and I'm done with this upper part. I mean, if it's 2, it's supposed to be a ketone, right? And well, RCOR, isn't it a ketone already? So we're done. How about this at the bottom? Again, a double bond is equivalent to 2. But don't forget that this time around, I have an extra H here that's hiding. So for the one at the bottom, we actually have 3. And if I use ozone and I have 3 oxidizable bonds, what's going to be the fate of this carbon? 3 ozone aldehyde. Meaning that this carbon at the bottom will be converted into an aldehyde. Sure. And this is the final product. So actually, it's kind of difficult really at first because there's a lot of chaos going on. But maybe if you watch this several times over, you will realize we're just following strict rules. There's nothing fancy here, nothing special at all. Also take note that we can apply the same rule to alkynes, not just alkenes. So just to add a quick one, let's say I have this very simple example. It's the most cliche one. And I subject it to oxidative cleavage, just OC. Either of the 2 reagents, it's going to be the same. Okay. Let's say KMNO4. And then I try to cut this into 2. First, what's going to happen to this half? Well, remember a triple bond is 3 oxidizable bonds, and then add this hydrogen so that makes it 4. And therefore, what will happen to this carbon is, well, it's going to be carbon dioxide. So the fate of this will be merely CO2. How about this? Let's look at this carbon. How many OBs does it have? 1, 2, 3. No H, so only 3 oxidizable bonds. And assuming that most alkynes actually become carboxylic acids if there are 3 OBs, all I have to do is to copy this CH3, and then this one will be written as COOH. That doesn't look nice. So maybe if I reverse it, it will just be more simple written as CH3 COOH. So see that even though this time we used a triple bond for oxidative cleavage, we followed the exact same table because that's the point of this table as a guideline regardless of whether you have an alkene or alkyne in front of you. Hopefully that this will help you in problem solving for oxidative cleavage. And we will revisit these slides when we go to redox of alcohols because, well, oxidations are always the same in definition. And I hope that oxidation has been clearer to you here compared to before. A little more concrete, yeah, more difficult, more confusing, but hopefully a little more expounded.